in school some definition of one. Okay, you first. What's an eigenvector? According to the definition you learned.
It's like a set of vectors for the matrix. If you multiply the matrix with the vector, it equals to like a constant times the vector.
Exactly. Okay. Yeah, so this is how everybody learns it in linear algebra. You have some matrix. We'll name this matrix M. And you have a vector. And usually when you multiply a vector by a matrix, you end up changing something about the vector. So if we've got a 2D vector, we multiply it by a matrix, maybe it goes over here now. It got a little bit longer, it rotated a little bit, it is a new vector. Some vectors are special vectors in that when you multiply them by a matrix, instead of rotating at all, they just move in the same direction and get bigger or smaller, or maybe they go negative. It's as if you multiplied it by a scalar. So we can say this is equal to lambda times v, where lambda is a scalar. And this, I remember like learning this in linear algebra and being super bored because it's just like, cool, I guess that's fine. You have this matrix, this vector that has this negative property, but it's not immediately obvious at all why this would be useful for anything. At least that was my memory. Maybe you aren't going to catch on. But it turns out that these particular eigenvectors that are only scaled by a matrix rather than rotated at all can be really useful for trying to characterize what a matrix is doing. And that's because the vector that has the largest eigenvalue captures basically the most information about what this matrix is doing to eigenvectors. So let's say, for instance, that this eigenvector, the one that I drew earlier, is the one with the very largest eigenvalue. So whenever, what we got here, and it's going to be like, what is that? 1, 1 is what this eigenvector is. And let's say it has an eigenvalue of 2. So that means m times v is going to just double the length of this eigenvector, but it's going to point in exactly the same direction. There's lots of other vectors in this space that the matrix might act on. And they might have something in common with this eigenvector. We'll project onto it a little bit. But then something in common with the orthogonal directions as well. If this eigenvector projects a lot onto this, if this normal vector projects a lot onto this eigenvector, then that means it's going to get scaled up a lot as well. So since it projects this much, we're going to double that component and then put it back. It also projects onto other directions that are not this eigenvector, so it might get rotated around a little bit. But the extent to which it gets, but basically, the more it aligns with this eigenvector that has the very largest eigenvalue, the more it's going to get scaled a lot. Any other direction can't possibly get scaled as much as this eigenvector does because it doesn't have the maximum alignment with this thing that has the largest eigenvector. This kind of necessarily bounds the way that this matrix can move vectors around. So the activity of this matrix, the thing that it does to vectors, is bounded by the largest eigenvector. The second largest eigenvector will bound it the second most, and so on. So that's one of the reasons that eigenvectors are important, is that they capture as much information as possible about what this matrix is trying to do to the vectors that it operates on. And so that's a really nice property. There's other reasons that these eigenvectors are nice too. So right now, we're only talking about just one eigenvector, but you can have a whole set of them that are orthogonal to each other. So you might, so not all matrices permit this, but some matrices allow you to get a whole bunch of eigenvectors, each of which has a different eigenvalue. And then you can write the matrix like this. We're going to call this V, this capital lambda, and this VT. And what this matrix is all of the eigenvectors just arranged as rows. So this will be V1, V2, and so on. And these are all vectors, so they point down, and that's what makes this a matrix. I'm actually going to draw it like that. So V1, and that points down, each element is the corresponding eigenvector. Or eigenvector, sorry. This matrix is just this one transposed. Basically what this means is that sometimes you can decompose this matrix M into a bunch of vectors that are all orthogonal to each other and all have the same length. They'll all be length 1. And you have this matrix that tells you how much each eigenvector gets scaled by the matrix. If you basically, all right, so when you're talking about this space, you have a basis that you're using to represent all of your points or all of your vectors. You have this x-axis and you have this y-axis. And using that basis, if you describe things as points in the space, sometimes you rotate things around, and sometimes you scale them. You basically do all of the funky activities that a matrix can do to things. You're not just scaling them. But if you represent them along this, in this basis, using the eigenvectors as the dimensions of your space rather than the natural x, y, and z axes, then you know that the things that your matrix is doing is just scaling each component, and you can consider the components independently when you're trying to think about how this matrix is going to behave. I've heard this sort of described as the right basis to use in order to talk about what this matrix is doing, because it operates on each dimension independently rather than moving mass from one basis function to another. So that's a little bit more complicated. I think the main takeaway is they capture in broad strokes what your matrix is mostly trying to do, and the dimensions that it will scale a lot. And then there's also this direction where you can think about it organizing the information in your matrix in a way that's a little bit easier to think about. It's diagonalizable. Any questions? Yeah.
Not a question, I guess. Sorry.
No,
never say that phrase.
You're moving up in knowledge, Julie.
I think you said earlier that each vector is length 1, but you meant each vector is long 1, not
yes.
a number of elements.
Yeah. So the norm of a vector. I was trying to be casual, I guess. The norm of a vector is basically the distance between 0 and the endpoint of it. Usually, yeah, so what it is equal to is basically the Pythagorean theorem, if we're using Euclidean space, which we are here. So if this is the x component of the vector, and this is the y component of the vector, oh, that's nice. You have to stay awake now. Then the norm is the square root of x squared plus y squared. If you have more dimensions, then it's the nth root of all of these terms. Sorry, squared still. I don't know why I wrote that. Cool. So this is basically just it's called the Euclidean norm. And the reason I referred to it as length is because it can be geometrically visualized as the length of this vector, the distance from 0 to the end. So I mentioned eigenvectors are those that are only rescaled by the matrix. In theory, this will hold no matter what length the vector is, right? If you have this vector, it only gets rescaled, and then if you have this vector, it also only gets rescaled. It's just a different scalar function. So to break the tie, usually eigenvectors are talked about as we're just going to say that they have to be length 1, and then we'll let the eigenvalue do all of the rest of the scaling. Keep and so that's basically controlled and separated from the possible lengths of the eigenvector. Cool. Did somebody almost ask a question? I feel like I saw a hand twitch and then. Yeah.
So there's a description of this that I've heard quickly, and can you just correct me if this is something wrong? The only way that I've heard you talk about is if you, not strictly analysis, if you think of a matrix as a function, it takes an output and drives it out. And the eigenvalue decomposition is essentially the steps that the function is doing that are independent of each other to give you the output. So you break it into the independent steps of what the function would be doing.
Yeah, so I think that's I guess this is sort of aligned with what I was trying to say about it being the right basis function to think about it. If your matrix is, it ends up rotating things and scaling them. But you can think of it as moving into this basis, basically saying I'm going to now describe every vector in terms of how much it projects onto every eigenvector instead of how much it projects onto the axes I started with. And then I'm going to rescale each of them one by the amount that the eigenvalue says to. And then I'm going to put it back. And so that's one way that you can think about what these eigenvectors correspond to, is like saying I'm going to work on this axis, and this axis, and this axis, and this axis, and in the end I will have created the right eigenvector. So when we decompose it in this way, this sort of corresponds to these steps. You can think of, if you were to multiply m and a vector together, this first one takes the vector and embeds it in eigenvector space. It puts it into eigenvector space. It describes it, how much it projects onto each of these dimensions. This matrix ends up just scaling each of these dimensions. And this one undoes the transformation and puts it back. So that's one way you can think of the eigen decomposition as opposed to the eigenvectors individually. Yeah, so these guys are great. So one way you likely have heard of eigenvectors is as principal component analysis. Has anyone done principal component analysis? I won't call on you already there. I'm just like wondering. I realize maybe that was tiny there. But okay, so a lot of people are familiar with principal component analysis. And so the way that principal component analysis is defined is as the eigenvectors of the covariance matrix of the data. In this case, n is equal to the covariance of your data. You start with a big data matrix with lots of samples and lots of dimensions to it, and you basically say how much do each of these dimensions vary together. And the dimensions that vary the most together will have large eigenvalues of the covariance matrix. So if something ends up being a principal component, that means it captures a lot of your variance, and we found that one by just picking the one with the largest eigenvalue. Is that a familiar version of principal component analysis, like eigenvectors of the covariance matrix, or not so much? Okay, more nods than not. Cool. So that's eigenvectors. Maybe we should try and revisit the code, and if that's not working, I'll do Laplacians. I feel like...
Does anyone not have the tutorial code? And
Did you say
We shared mobile hotspot and then download it like that, so if you can
well,
share
does
mobile hotspot.
of the people who don't have it, do any of you have Macs? Who does not? Or you know. Okay, I don't know what the Windows solution is. It has a USB thing. There's AirDrop.
Yeah,
So if you
see an airdrop from an anonymous computer, I'm not sure if I can accept it. Is that it?
That's how they get you.
Yeah, it's probably no one in this room.
It's a Russian virus.
So the additional issue is people will need to have network X as well, which if they don't already have might require internet. Yeah. We can try and
download it in a conduit, it'll have network built-in, or if you've got the container, it'll have network
I don't think so.
If you guys have Macs, I can do AirDrop. I've done a few that it's on the network. And then everybody else, I've been passing around USB drives. It's only 40 megabytes, the zip files.
I can AirDrop you Network X also if you want. You all.
Oh, it looks like it does. Yeah, because it has the icon distribution.
Oh, great.
So it just
Ah. So if you have the Docker image, it supposedly has Network X on it. Oh, but the whole point is
well, I just opened the Docker and looked, and it showed for me.
never mind.
I just did 2 and I didn't see it.
Yeah, just decline if you guys don't want me to send you rain.
What's the name of this?
I think it's just like Wu Ching, it's something unimaginable.
I don't see it now.
Oh, no, it's not.
Yeah, it's on the.
Yeah.
Oh, here we go.
don't like contests very much, and I don't have contests that are
Can-
so I don't.
You put it in the mind, doesn't it?
I put it in the slide channel.
Oh, but it's not on the
It's not on the.
Oh, okay, sorry, the file I just sent is not in there.
If you open the notebook in the container, it has network X in it already. So it should be
Alright, sorry, whoever I sent those files to, I'm gonna send a new one, it's even smaller, so it should be, that's apparently Mark's, not. And that's, sorry, if anyone has the flash drive, if they could also, upload the right file to it, sorry again.
So the new one?
It's a really small file.
You're ahead of where everyone else is.
Is there any other flash drives I can add the files on? Pass around? We got one. Is there another one? Oh yeah, you're okay, great. Does anyone need, who hasn't gotten it yet? Back here.
Here's another one. So this is like is that oh, you don't have to. You need a couple packages. Once you have that, it's the small one.
This is going to require network access to, I mean, outside of the network.
Just the, but it's using your local
Anyone else delete the files? Everyone else has it, or is good with not having it? I guess it's in the Slack channel. She didn't upload the GitHub. No. Well, each one needs to everyone needs to
Oh yeah. Yeah. That was good. It was like the very
Anyone else? Otherwise, I think we're good. Yeah? That's not a lot of head shaking, but I'm just gonna guess.
All right, so I'll walk you guys through it, and then I'm hoping that we can just have some exploration of the code thereafter. First, we import a bunch of things, and a lot of these are functions that I wrote for different purposes. So the first thing is tasks, and that has a bunch of functions for generating graphs that correspond to different discrete environments. Representations has code for taking in the matrix that specifies these environments and producing a representation of each state. There's a couple of different ways to do it. There's some plotting functions for visualizing results. There's util, which does literally nothing interesting, but it had a function I needed. And there's RL, which is useful for learning value functions given the features. So are all those imports working for people? This will indicate if you've successfully got the dependencies and everything. Wow, I didn't expect that to happen. Okay, cool. You guys are so good at installing network X. All right, so in this following section, there's basically parameters that I've set for a bunch of different tasks. We can go back and change these parameters later and look at how they affect things. And in the following panel, there's a bunch of different types of tasks that I will describe to you. You can also guess. They should be fairly obvious from the names. So the first one is a line. That's a bunch of states that are connected to each other in a line. The next one is a ring. It's a bunch of states that are connected in a ring.
What?
I know. I thought of naming it like I don't know. So the one after that is an open room. It's also an open rectangular room. It is in contrast to a compartmentalized room where there are 4 different compartments called 4 rooms. Then I accidentally wrote ring for clique, so feel free to change that. And this gives you a clique. What a clique is a bunch of nodes that are all connected to each other. So every single node is connected to every single other node. A clique ring is when you have a bunch of different clusters that are all connected to each other in a ring. So you've got like 5 nodes connected to each other, and they're connected to another group of 5 nodes, another group of 5 nodes, all around. What that's useful for is just being a graph that has clustered community structure. The next one is Tower of Hanoi. This one is one of my favorites. It's the task graph that underlies this classic problem where you're moving disks around in order to satisfy something. And if you plot the structure of it, it has this like recursive triangle structure where you have triangles that contain triangles, and it has this multi-level cluster structure, which is kind of nice. The next one is a tree. You can specify how many branches and how deep it is. And finally, we've got a stochastic block model, which is also another graph that's supposed to capture cluster structure, but this one a bit more noisily than the clique. What a stochastic block model is you basically specify how many clusters you're going to have, what the probability is of being, and what the probability is of an edge joining nodes that are in the same cluster or different clusters. So generally, within clusters should be a higher probability, otherwise you may have a weird graph.
Yeah, what's the difference between tree and clique?
So trees and cliques, what cliques are is a bunch of nodes that are all connected to
I
each
know
other.
what they are.
Okay.
And you said something about tree is like the clique structure, but something else you said?
No,
Okay.
I didn't mean to say anything like
Okay.
that. Trees are very different than cliques.
Yes. Okay, good.
Almost everywhere. Cool. So we're initialized to Tower of Hanoi, so go ahead and run that. If you want to see what it looks like, hit the next panel. Each of these nodes are colored according to hard-coded labels that a lot of these graphs have assigned to them. And then in the next panel, you're going to pick your chosen representation. And it's initialized to a random walk successor representation. The other options are one-hot, which is just each state is represented as an index, and Laplacian eigenvectors, which are some of the eigenvectors that I talked about in my talk, and Euclidean Gaussian. And the way the Euclidean Gaussians work is we just take a bunch of random locations in the state space, and it's basically the way a place summing works. We have a bunch of locations in the state space, and it has a receptive field that falls off as a function of Gaussian based on its location. And then if you want to see what some of these representation features look like plotted over states, you hit the next panel. And you see what a successor representation looks like, what each column of the, or sorry, what each row of the successor representation matrix looks like. Basically, for every state in the environment, it has some activity under one of these features, and that'll be plotted in each of these panels. So if you plot successor representations, you get these very localized blurry fields. If you switch it to Laplacian eigenvector, you get things that look a bunch more like waves. You can see they extract some of the cluster structure. If we use Euclidean Gaussians, you'll get things that are sort of centered at points in this space. It looks a lot like the successor features, except they will not adhere to boundaries quite so well. So that's a thing we can play with later.
Kim?
Yes?
So, each plot is a value in the successor representation, like, right?
It's a row.
Or,
It's, so each of these plots is actually a column. So basically, this might be easier to visualize with the Laplacian eigenvectors actually, because those were the ones that in my presentation were like super vectory. But basically, what each of these plots shows is how much is one feature going to be activated at every possible state in your environment. So each, for the successor representation, what that means is each feature has some state that it's trying to encode predictions about. So you're saying, for that one feature that has one preferred state, how much is it activated by being at every other state in your environment? And states that are nearby are going to activate it a lot because they tend to predict each other, and states that are far away are going to activate it not so much because they don't predict each other until really far in the future. Yeah?
Question. Does this have a minimum Python dependency? I'm running 3.5 and getting a traceback error about network X not having an attribute from the array.
Oh, is it a warning or a full-on error?
It's a full-on error.
Interesting.
Won't let me call anything.
Let me check what version I'm using.
Which is fine. This is me.
Well, it's not ideal. I'm using 3.7.
What version of network actually running?
Me?
Well, I can do. Yeah, I guess.
I think I'm using 2.3.
You're using, do you know what version of network X you're using?
Whichever one on the automatic cells.
So, what is the, yeah, what is, maybe it's an easy one.
Yeah, correctly.
Trying to do it. Do you mind if I just take stuff?
So is this the first place you saw?
Do you have the...
yeah, I mean, what about this?
And you just downloaded thinking? Is anybody else having an error with network X? So while we debug network X, I'm going to just walk you guys through the rest of this, and then I would just start playing with the graph. So this function will plot the centers of the Euclidean Gaussian place cells, if that's the representation you're using. If it's not, it doesn't do anything. If you're using an eigenvector representation, this will plot the different eigenvalues. Doesn't do anything. And then this function will train
Sorry,
up.
what does plot centers do again?
It plots the centers of the Euclidean Gaussian place fields if you're using that as your representation.
But not if you're using SR.
If you're using SR, there's like no plots.
Exactly.
Yeah.
So this is like the paper that Nathaniel had a while back where they use Gaussians.
No. So that paper, I was thinking of implementing that, but I didn't have time. So in that paper they use geodesic Gaussians, not Euclidean Gaussians.
Oh, I see.
So for that one, with the case of Euclidean Gaussians, the receptive field falls off as a function of location in Euclidean space. In Nathaniel Dawes' paper, it falls off as a function of geodesic distance, which means distances stay in the graph. It uses the shortest path distance in the graph.
Why is it plotted? I don't understand.
Plot centers.
Yeah, so I plotted.
Okay, so change representation name to Euclidean Gaussian.
Yeah.
So if you plot it, you see there's a bunch of random dots all over the place, right? It looks like that. Each of these dots is the center of some Euclidean Gaussian place field. Because each of these states has some position in XY space that's being used to determine their distance from these Euclidean Gaussians. Yeah.
Do you mind explaining, so if you were to visualize the Laplacian eigen for the feature, can you explain how to read this when you, yeah, exactly.
Sure. Yeah.
I think I understand the other ones, but I don't know how to read, yeah.
So each feature of your representation corresponds to one eigenvector of this matrix called the Laplacian. Each panel here basically corresponds to one eigenvector, and we took every element in that vector and plotted it over the corresponding state. So this, you can think of this as a heat map, where if an eigenvector has a really negative value at some state, then it'll be quite blue, and if it has a really positive value, it'll be quite red. Each of these panels corresponds to a different eigenvector, and we're plotting it out over the graph so that you can see what this, basically like how this eigenvector will represent every one of these states.
Why are there 16 letters?
Because I happen to plot 16 of them. So if you want to see a different number of them, great question, glad you asked it. If you want to change the number that you look at, you can change n rows and n columns. Yes, yeah.
So is that where they get like increasingly high spatial frequency?
Yeah, exactly. So the first eigenvector will have a very high eigenvalue. A generally high eigenvalue. When you use the successor representation, when you use the Laplacian, this transfers to being a low eigenvalue, but that's kind of just a confusing thing. These low spatial frequencies will try and change as slowly and as smoothly as possible over the graph. So that's, yeah, I think like, you don't really start to see wave structure until it gets a little bit more high frequency. And that's easier to visualize if we look at a line.
So is it fair to, so like, if you're visualizing the success representation, you're sort of like, I'm here, here's the sort of expected value, expected probability of visiting these places, which are sort of smoothing off as I get farther from where I am now. Is the way to read this like, the first couple of eigenvalues here are like generally moving in this direction, generally moving in this direction, and then as you gradually get farther and farther down, you're sort of making specific angles based on where you are. Is that?
That's exactly how I would think of it. The first ones basically capture, like in broad strokes, how states can be distributed and separated from each other. So it'll try and change as slowly as possible over the course of your graph. If you're using this, therefore, to like represent your graph, then it ends up separating states a lot. As you start looking at the higher frequency eigenvectors, they go up and they go down, and they go up and go down. And if you organize states according to them, you'll end up moving states far away from each other that are close to each other in the graph. And this can be useful if you want to account for information at very high resolution. If you want to be able to tell the difference between one state and its neighbor, you want something that's high for one neighbor and low for it. But when you want to just get the macroscopic global structure of the graph, then these first couple are useful. So one thing that might be nice to look at these is to start with the line example. Because, so if we go up to task name, and change it to line. And if we plot it, you see you've got a bunch of states in a line. Then if we look at the eigenvectors, you can see they look a lot like cosines. They look like sinusoids. It'll go from blue to red, then it'll go red, blue, red, it'll go blue, red, blue, red. These end up having this like nice wave structure. So when I kind of refer to these as waves or like changing slowly, this is the easiest to visualize over something like a line. The ring and the rectangle also illustrate these properties kind of nicely. And then you can sort of see this effect happening at the funkier graphs too, where they try and change slowly and like separate things that are really different. Yeah?
So I guess I missed this in the beginning. So how many eigenvectors do we get maximum?
So if you have an n by n graph, or sorry, an n by n matrix, then and it has some nice, it has the right properties, then you can get n eigenvectors. You'll need n to like span it fully to capture all the information.
Right, in this example.
So in this example, let me see, how many states did we use? So since there's 32 states, there should be 32 eigenvectors total.
And 32 is the number of like circles
Yeah.
along the line.
Yeah, exactly. So if you want to see more of them, you can change n rows or n columns, and it'll plot the even higher frequency ones. Yeah.
So my plot representation features doesn't look at all like that, and I think it's because I have a different color palette loading somehow.
Oh, that's weird. I thought I manually set the color palette. But what you can do is change CMAP equals capital R, lowercase d, capital D, lowercase u, and that should not work. Interesting.
It might be blue red.
No, I think I just didn't. This function just doesn't take a color map.
You just need a
Let's.
You can set it with C1.
What's that?
You can set it with C1.
Yeah. So I'm basically it's easy to set up a color map. It's just I didn't happen to set up this function to take one in because it's set in a deeper function.
The function sets the color map based on features.min.
Yeah.
So red, blue, or C1Q helix.
So is anybody else having this particular issue with the plotting? Are those raised hands? Okay.
You change to the path because that's what I did.
So
change to the path.
what I would do is just this. Let's just open the.
So before it was set to RW successor rep.
What's that?
And I changed it to the path in Exactly. I was wondering if it looked different for me, and then I. Yeah, so it's about what.
We got it.
Got it? Okay. Does everybody have it? Cool. Okay. And since we're in eigenvalues now, we can look, or eigenvectors, we can look at the eigenvalues. This is sort of what those look like. They have a very smooth fall off in the line.
sorry, why are they increasing by equations that they should be decreasing?
Yeah, so basically there's I glazed over a little something with the eigenvectors. So basically the way I introduced eigenvectors was to say like the eigenvalue captures the thing that changes, that vector changes the most. And the transition matrix, the successor representation matrix and the transition matrix share its eigenvalues with the Laplacian. But one thing, but they end up being sort of an inverse of each other. So whereas the biggest eigenvalue of the transition matrix is the thing that changes the slowest. It captures the most variation in the transition matrix. That corresponds to being the smallest eigenvalue of the Laplacian. And that's because the Laplacian ends up capturing the force of diffusion. And the thing that changes the most and captures the most information about the transition structure is the thing that changes the most slowly under diffusion. If you have like a very high little peak and you start letting material like randomly walk away from that peak, it'll change really quickly. But if you have something that's like a really broad low function and the material starts kind of randomly diffusing, that'll take a longer time to go away just because it's already really spread out. There's not that much that entropy can do to make it go away faster. So things with small eigenvalues capture coarse structure and are the large eigenvalues of the transition matrix. And before we go on to the next one, I think one good one to look at is the, let's do the clique ring. So if you look at the task, this is the structure of a task that Anna Shapiro used to look at encodings of event structure in hippocampus. So the task that she did was she had each of these states was associated with some fractal, and the subjects would bounce around from fractal to fractal, experiencing different things. And unbeknownst to them, there was this event structure where if you were in one cluster, you tended to stay in that cluster just because there's a lot more ways to stay in the cluster than there are to leave it. So you'd end up kind of seeing a lot of blue things for a while, a lot of purple things for a while, and a lot of yellow things for a while. They weren't expressly coded that way in the task, but the statistical structure emerged. So if we look at the eigenvectors of them, you can see they sort of capture this clustery structure in a way. You see for the first eigenvector is almost always meaningless, but the second one will say, will be very red in this top corner, very blue in this bottom corner. And then the second one after that has sort of a rotation of that where it'll be very red up here and very blue over here. So these end up basically pulling apart different clusters. If there is no cluster, if you just have something homogeneous like a line, then you'll get these slowly changing Gaussians, or sinusoids. But when you start to have clustered structure, then these tend to stay within cluster rather than blurring over that line. And that's because if you're doing a random walk in here, it's very rare that you're actually going to randomly walk out of a cluster. There's only a couple ways to get out, and you're usually not going to take them. So diffusion is going to move you very slowly over these boundaries, and that's why you end up with this clustery structure.
Why is it often that the first eigenvector is just like the main one?
So the first eigenvector is always 1 everywhere because the rows of this matrix sum to 1. So if you multiply a matrix times just a vector of 1s, it has the effect of just summing up every single row. You multiply them by 1 and then you sum them all together. Since all of the elements, each row of this matrix sums to 1, or then you'll end up just getting, sums to 0, then you end up getting a 1's vector as your first eigenvector. The reason I said almost always is that if you have like a graph that's in 2 completely different pieces, then your first eigenvector will be 1 for the first graph and then 0 everywhere else, and then the second one will be 1 for this graph and 0 everywhere else because you don't transfer anything between these two.
So Kim, if you, there's like with the usual eigen decomposition of the Laplacian, there's this idea of the second smallest eigenvalue being correspondent to giving you the number of clusters and things like that, which we do in spectral clustering. Is there correspondence then in this version?
Yeah, so the reason that this second eigenvector is so special that it has a name, it's called the Fiedler vector. The first one sums to 1 everywhere, or it just is 1 everywhere, it's not very interesting. But the second one, because it has this structure where it tends to stay in one cluster and separate different clusters apart from each other, it ends up being an approximate solution to this problem called the normalized min-cut. And what this problem is you want to take a graph and separate it into different pieces where you have as many nodes as possible in each chunk and as few edges as possible combining them. You basically want to find like the natural way to cut a graph in half without segmenting too many edges. And it turns out that this second eigenvector gives you an approximate solution to that. If you threshold it at its mean, and you take everything that's greater than the mean and put it on one side, and everything that's less than the mean and put it on the other side, those edges you cut will be an approximate solution to this problem. The actual problem turns out to be NP complete, but this is not a bad solution. The intuition that I have for this, at least, is that it's because you diffuse very slowly over these rare edges that connect different clusters. And yeah, I think there's also, if you ever do spectral clustering, you'll embed in these eigenvectors and then apply a clustering algorithm because they're so good at splitting things up. And if we look at the eigenvalues for this one, we see they're a lot chunkier. They don't change quite as smoothly. We also see that we have a lot of repeats. The first two eigenvectors have exactly the same eigenvalue, and same for the next ones. And that's because this graph is very symmetric. If you look at these first two eigenvalues, or vectors, they're basically just like rotations of each other. So they're going to have the same eigenvalue. That can be important for a lot of stuff. Cool. So then the last part of this.
I'm going to ask another one.
Yeah.
So in the sort of eigen option framework, there's a ton of options that are useless, basically. So there's a lot of eigen things that can come up that are not really useful for either subtle setting or clustering.
Yeah. So I really think the reason the eigen option thing works is it approximates Lagrange. If you are sampling randomly over your eigen options, then you're going to end up taking long jumps preferentially, and they respect the topology. So there's a lot of these low ones that if you sample them, just like you do multiple things that aren't that useful. And if you were doing the proper Lagrange transformation, I think they get squishy more. But I think they basically not to like the diffusion aspect of it, where you sometimes take big jumps, but usually you want to take little jumps and actually explore areas. This is kind of about I don't want to say it's not like I don't know. So it seems like that.
I think you are helping Dave. What I want to ask was not actually, I was going to ask, is there, outside of the framework, is there like other uses of all the other ideas?
Yeah, so they basically are useful for capturing higher frequency information. If you want a really low dimensional representation that captures the given certain assumptions about what kinds of functions you need to fit, you might be able to discard some of them, but it would be risky. Like you would have to, like for instance, maybe if you know you're only capturing regular symmetric functions, you could do something different like that. That's one thing we're exploring with respect to like grid cells being hexagonal or not. But yeah, generally, this is a complete basis for like all the functions you define with the graph. Cool. Okay, so the last part that I want to leave you guys with before, just to like walk you through this, is this last function which lets you train up a value function using some feature space. So I had the figure in my talk where you're learning about the different dimensions of a feature space rather than learning about each state one by one, and that's what this function lets you do. In order to see what it looks like to learn about each state one by one, set your representation equal to 1. That represents each state as its individual index, and you'll see how fast does learning happen if you're just doing that. And this is a sort of like abbreviated RL agent. We're not really trying to do, there's no control in it. We're not trying to do the whole like action selection part of this. We're just showing how this affects the learning of a value function. So it's more about generalization and like really closing the loop. And so these are the different parameters of the learning process. And given whichever representations, it'll be different. If you go to the next function, plot weights, it'll tell you how much does the value function project onto each of these dimensions of your feature space. If it has a really big weight, that means it's a really important feature. If it has a tiny weight, it's probably not that important a feature. And if you want to visualize value, you can do this next function. So the first plot above will show you the value over states, and then the second will show you the ground truth. And then if you want to, as like sort of a heuristic for how good the value function is at every point in time, you can look at how much discounted reward you would get using this value function at any point in the learning process. And so you can see that curve goes up, and it goes up at this rate. If you use a different representation, it'll go up at a different rate. Maybe it'll be better, maybe it'll be worse.
Sorry, the ground truth value over states, where is that coming?
So for ground truth value over states, we just used, if it knows where the reward is in the environment. What is the value?
Reward is just arbitrarily being assigned to a single state.
Yeah, exactly. So if you want to change what the reward function is, you can mess with reward dec. This is a vector that has the reward that is found at each of these states. It's deterministic in this case. And the way we set it up here is you just have one index that's rewarded. It's the last state in every graph, but feel free to play with that. And we start in current state, which is 0, change time steps 2. And then the start probability is for hitting ground truth value. That is not useful. That's something I was using for. So one other thing that might be fun to look at is what happens for the tree. In this case, the eigenvectors pull out very hierarchical elements. So you can see the first eigenvector will separate the two halves of the tree, and then going on from there, they'll do more fine-grained partitioning of the tree leaves, which is useful if you want to have like a hierarchical representation of the decisions you can make. How much time do I have?
2 days.
2 days? Okay, cool. In that case, we'll painstakingly go through each of these graphs and every representation. Yeah, I guess I put at the end some things that like might be fun additions to this script if you guys want to like have personal challenges or whatever. Throw Excel for or something. So comparing different representations and how they affect learning and how their value functions might look different. One thing you could do is also limit the number of eigenvectors you're using, truncate that matrix at k, and see how well you can approximate the learning function. If you can try and find a reward vector that works really poorly with some representational basis. For instance, if you're only using the first couple of eigenvectors and you have a reward function that changes really quickly over space, this is going to have a hard time learning it, and that might be a good thing to visualize and get comfortable with.
Can you explain the value function we know?
Yeah, so in the following plot, we see the value function plotted over states in the graph. So every state is associated with some value or expected reward. And that's basically like value over each state. If we represent each state in terms of its features, then we end up, instead of saying like how valuable is each state, we can say how valuable is each feature.
And what are the factors?
So in this case, the features will be a Laplacian eigenvector. In that case, you're saying like, what is the weight on that eigenvector that I need in order to approximate the value function? So if you look back at these plots, it's basically saying I'm going to scale each of these by that weight and sum them together, and then that's how I compute my value function. But these are sort of like the basis components that you really combine. So what ground truth value? Yeah. So basically, what I'm using for ground truth value is if we just use the transition matrix for this graph.
Multiplied by the rewards.
Yeah, so we're doing, instead of just multiplying by reward, we're basically saying like, what is the expected reward you're going to get starting at each state following this policy. So if you actually, with the training loop, you don't know where the reward is. And you don't know how valuable each state is made as a function of this reward. But if you did know that, then that would be ground truth value. Does that make some sense?
What's the
So you're not learning the value function, you know the value.
So ground truth value does not learn the value function. The value is the learned value function. Yeah, that's just sort of like, given the dynamics of where reward is and what discount I care about, how much, and a uniform probability of starting in every state, how much reward should I be getting if I'm doing the best possible thing.
So the features can be defined based on SR, or they can be defined in terms of the eigenvectors.
Yeah, so the...
that might be interesting also, like another way to compute this would be using the SR instead of the eigenvectors.
Yeah, so in that case, the reward weights you get should correspond to just the reward at every state, if you're using the successor representation. The other thing that might be interesting to look at is in multi-compartment environments. That's when you should start to see a difference between using a successor representation versus using Euclidean radial basis functions, or Euclidean Gaussians. Because Euclidean Gaussians will blur over boundaries, but successor representations won't. So you should generalize differently in these contexts. Yeah, for the four rooms environment is nice for illustrating that.
Tree example shows a really big difference depending on the basis of them.
Yeah, that's interesting. That makes sense. Yeah, that's interesting.
That's very fun, actually. And you would expect this from our, and if you have a neural measure, a behavioral measure, and then you can compare these things. I think our claim is that the hippocampus would look like not a Euclidean, but the successor representation.
Yeah, yeah.
Which goes against the other claim.
Yeah, and so there's also like, I made some decisions about what the natural XY coordinate of these locations were, that based on like how I would embed them in space, and that'll factor into the other. Yeah, so I guess this is kind of the tool I wish I had when I was starting to play around with representation learning, because it's like, the kind of classic question with it is like, how well does learning get supported by the representation I picked? Like, is it generalizing the right way? Is it not generalizing the right way? Is this speeding up learning, or is it actually not speeding up learning very much? So I think that's...
Actually, sorry, could you... I can't hear.
Go on, sorry.
Okay, yeah, so, yeah, that's basically, I wanted to provide you with this tool, give you an opportunity to explore it a little bit. But I feel like we have used about an hour of this, so I'm happy to take it offline. Yeah, do you?
I'll ask you.
What's that? Did you have a question?
I'll ask you after.
No, we appreciate the...
I was just gonna say, I'm just getting some errors trying to run the open room to see the value.
Okay, I will...
No, it should be, no.
Yeah, I guess let's talk about it later. If it turns out there's a bug, I'll just like fix around. You have a question?
Yeah, I guess I'm a little unclear about exactly what you mean by the word representation here. Is it like some kind of information about state transitions? That have different shapes, or how?
So basically, what I mean by representation is that each state can be described by some vector, and that vector might just contain only the information about which label that node has. It might be just a one-hot, which is 0 everywhere, except for an index which corresponds to the name of that node. Or it might capture some additional information about that node that's useful, that might inform learning. So all of these representations that we're using capture information about the transition structure. They tell you something about how one node relates to other nodes. So for instance, with a successor representation, you're representing each node in terms of how much it predicts other locations. Every element in that vector says, how much is some other state predicted, given that I'm in this current state now? With the Laplacian eigenvectors, you're also saying, like, given we have these functions that change slowly, am I in the middle of this, or am I at one of the extrema of the graph? Where am I relative to the dynamics as they're changing across this graph? With the Euclidean basis functions, it's where am I with respect to all of these randomly placed localizing functions that I might have. But what I mean by representation in this case, like very concretely, is it's just the vector that describes every state. And then when you're learning about value, instead of learning about each state individually as an index, you're learning about the features that you can use to describe each state.
So when you use the one-hot representation, that's basically learning each state individually.
Exactly, yeah. If you have two different states, their one-hats have 0 overlap whatsoever. One will have maybe a 1 at index 30, and the other will have a 1 at index 45. And the overlap between those states will be 0. But if you have two states that both predict the same outcomes, they have a lot of overlap. If you learn that one is associated with some reward or some future value, then you want that information to be broadcast to the other states that have similar features representing them. So that kind of overlap in state representation tells you about how you should generalize information. Yeah?
have you been able to construct problem examples where, in fact, you learned the wrong thing?
Yeah, for
like
sure.
Superstitious examples, and can you use those to essentially test these? I mean, all of these are approximations to correctness. Right?
Yeah, so I mean, I think especially, this is one of the risks too of trying to do this from a machine learning perspective, is you're always just like, what's the best possible thing? Like that's probably the thing that's right. But what you want really is to like try and find situations where you can mess it up to design better experiments. One thing, there's definitely a bunch of representations that do a bad job for particular tasks. So one thing, for instance, that's particularly susceptible to this is if you have a successor representation that predicts, I'm always going to go to the left, I'm always going to go to the left. Like with time you just learn, I never don't go to the left, so it just puts all of the predictive power on the left. Then if someday reward shows up on the right, you have no expected probability of going there, and it takes a really long time to learn that that state is now valuable and try to update your behavior accordingly. It sort of overfits to these examples. The other example that you see this in is if you use truncated eigenvectors. If you just say, I'm going to cut these off at some index, and you either pick an index that separates things with the same eigenvalue, you can start getting asymmetries in your space that you don't want. That's like a little bit more niche. Also, sometimes just truncating rather than using a gradual fall off can lead to weird effects in the boundaries. This is sort of the same reason people use wavelets instead of short-time Fourier transform, if that's a familiar debate to you. Yeah?
Just a very, very general question. Is there sort of like for specific task reward setting, is there an optimal representation that you can?
Yeah, so it's, I guess the optimal representation will depend a little bit on the distribution of tasks that you have. So you basically, the way you might set this up in like a meta-learning setup is you'd say, I have all of these different places, I have some expectation about where a reward is going to be in my environment, and I want to set up a representation such that it can move towards learning each of these value functions as fast as possible. In some sense, yeah, I guess having the optimal representation is sort of just like the value function if you're only going to have one value function ever, because then that's just like one value for each state. But yeah, I guess the extent to which there is an optimal representation means you would want to know something about what the learning process is likely to be and capture all the relevant information. Yeah, I guess one more thought on that. I think like this notion of like relevance from information theory and information bottlenecks sort of formalize this, has a lot to say about like what the optimal representation is. But basically you want to try and keep all of the information that's relevant to your value function and discard all of the information that's not. And if you maximize that ratio of keeping relevant and discarding irrelevant information, then that's like the optimal representation. Yeah?
So does it matter if you normalize the Laplacian or don't normalize it? Give you different representations?
So where it starts to give you different representations is when you have very, very variable degrees in your graph. So what's one thing that's common to do is to normalize the Laplacian, which is basically like if a bunch of nodes, you divide every row of this matrix by the degree of its corresponding node. The degree is basically how many neighbors it has. Where this starts to make a difference is in graphs that have really very different numbers of nodes connected to each other. So in most of these like spatial contexts, almost everywhere you have the same number of neighbors, and it's really only at the boundaries where you start to get effects. With like the stochastic block model, you have a lot more variability, and it'll start to make differences. Basically, like my observation is in broad strokes, it still captures the same things, but you get where you start to see differences is at these things that have extreme numbers of degrees. So like you can have a corners or something. Yeah.
Very basic question. So in the feature plot bars, how are the features ordered?
So the features are ordered, so they're ordered the same way they are in rep features matrix. So for the eigenvalue, or for the eigenvectors, they're just ordered by eigenvalue, increasing eigenvalue. For the successor representation, they're ordered by state. For every state, there's a different successor representation, which says like how many times you get to visit it.
So they're not ordered by the eigenvalues here?
No, they're only, well, the only case where we have eigenvalues is the eigenvector case. So that's when it's organized by eigenvalue. In all the other cases, it's organized by whatever organizing feature seems natural for the representation space. Usually that's staying. For the Gaussians, it's their random center, but those are yeah.
So for these examples, the adjacency matrix is symmetrical, but there are situations or MDPs where the adjacency is not symmetrical, then the eigen decomposition of the transition matrix and the successor representation will be different.
Yeah, so for the dimensionality reduction part, you can just do singular value decomposition, and like that story holds. But then, as there's all these nice connections you can make with the eigenvectors, and those don't hold. Those basically like don't hold quite so well.
For the non-symmetrical.
Yeah. So that's one of the reasons that like we use the random walk for a lot of these examples. Is like we can draw a link between the predictive representation, the dimensionality reduction, and then these other nice tools. When you start to have a really directed policy, then you basically don't get nice eigenvectors necessarily. You might get degenerate eigenvectors, and you need to use a more general method called singular value decomposition.
In that case, though, it might be that the new results that grid cells rearrange around the locations of rewards. This would be predicted from a policy-dependent SR, not a random walk that does move towards a particular direction.
Sort of. So basically, if you just have a policy that moves in a particular direction, your eigenvectors will just be 1 at the final location and 0 everywhere else. Because the thing that's stationary under your dynamics is being at the reward. Anytime you're not at the reward, you're going to move to the reward, and you only really like stay the same. You only rescale when you're just like at the reward and just consuming.
But if you explore the environment, it's not exactly.
Yeah, if you add a lot of exploration to your policy, then you sometimes get eigenvectors that aren't totally degenerate and are just like a little degenerate.
Exactly.
Yeah, we have a lot of this, but I think the stuff. Yeah, I guess there's other ways that eigenvectors might encode this by maybe warping space around reward locations. It's sort of a different pattern.
Which would still be different from being the eigenvector of the transition matrix, because it's no longer equivalent.
Yeah, that would be now the eigenvectors of a different matrix that's trying to capture a lot of information.
Yeah, so both of them, it's no longer the eigenvector of the transition matrix. That's what I'm trying to say.
Yeah.
Exactly.